In this video, we're going to do a brief overview and review of transformational graphing. So before we get into the graphing, I want to go through just some things that we sometimes take for granted when we're talking about functions. We want to make sure we're on the same page. So when I'm talking about a relationship or a function, and I ask for the domain is the set of input or argument values for which the function is defined. Typically, these are the x values. For range, the set of output values for which the function is defined. So domain is the input and range is the output. And like I said, typically domain are x values, range are y values. So when I'm talking about transformational graphing, what I mean is what transformations are happening to a parent function. And so if I have this general form of an equation using any function type, these various coefficients are going to have an impact on how that function is transformed. And so let's look at a demonstration. Notice here that I have a function, and if I change the a coefficient, you can see that when I change the a coefficient, I have a vertical stretch or compression. Now when I get below 0 and negative, I have an x-axis reflection. When I change this b coefficient, I'm being stretched and compressed on the x-axis, or the horizontal stretch and compression. When I go negative here, this is a reflection over the x-axis, or I'm sorry, the y-axis. A would be a reflection over the x-axis. When I change c, I'm translating to the left or the right, which is impacting my x values. And then when I change the d coefficient, I'm translating up or down, which is having an impact on the y values. The only new piece of the graph that we're really talking about here would be that b coefficient where we're having horizontal stretches and compressions. So the other piece is, when is a relationship or a function one-to-one? So one-to-one means when every element of the range corresponds to exactly one element of the domain. In this example that I have here of a relation, it shows you where the x values all go to a singular y value. Now a graphical representation like this parabola, we would use what you probably heard of in middle school called the pencil test, which mathematically is called the vertical line test, meaning that if I can lay a pencil down on a graphical representation of a relationship, and it does not cross the function more than once, then that function is one-to-one and is in fact a function. So now let's actually talk about some different function notation items. So looking on some of these guided notes, I asked for the domain of g of x. Now notice g of x is not a particular function that we know of, so because what we're looking at is just being able to identify domain and range values, so this is just a piece of relationship. Alright, so domain of g of x is, like I said, the input values or the x values. So we want to first use the correct notation in defining the domain. So I'm using function notation, which uses curly brackets. And I would say that the domain values are defined as x, such that x is between, and I would count on the x-axis for what the domain of each of these, what the domain of this function is. So if I were to count over to the far left of the x-axis, I would find the minimum value of the domain, which is -8, and then count over and find the far right, the positive values, for the domain 7. And so we would just express it that x is between 8 and 7 using an inequality. We would do the same for the range, but instead of using the x values, we would define it as the y values. So the range is defined y such that y is between -5 and +8. So then in part C, we're asking, okay, well, if I have an input of -7 or 0, what is the output? So if x is -7, what's the y? So if I count over to -7 and then down, I get an output of -1. Likewise with 0, if I go to an x input of 0, I have an output of 0. In part D, it's giving us the latter, and we have to find the argument, or the x value. So given a range, find the domain. So if I have a range of 8, I look on the y-axis to 8 and go to that point where the function crosses on the y-axis at 8, and I see that my x value when y is 8 is 5. For when the range value or the y value is -5, I would count over and find that my domain value or input value would be 6. In part E, it's saying find the range when the domain is 2, or I'm sorry, find the output when the input is 2, and add it to the output when the input is -4. So we would break this down. At 2, the output is 6, and I would add it to the output at -4, which in this case is -3. And so when I add these together, I get a positive 3. So then in part F, for what values is g of x less than or equal to 0? So this, looking at this function, we want to say, okay, when is the function below 0? When is it negative? So in this case, it is between the values, and if I count over to where it crosses the y-axis, -7 and 0. Now, had it asked me when it's less than 0 by itself, not less than or equal to, I could not include the values -7 and 0 because at -7 and at 0, the function is 0. And so in this case, it's asking when is it less than or equal to 0. Part G, we're going to omit. And then in part H, it says, is g of x a one-to-one function? Explain why or why not. Once again, one-to-one if you allow it to pass the vertical line test, or every input has a unique output. Yes, it does. And that's how we would explain that, is every input has a unique output. So now let's actually look at the graphing side of this. So given a function h of x, state the domain. So in this case, I would count to the far left on the x-axis to find the most negative point of the domain, which in this case is -5. So using the proper notation, I'd say that the domain is x such that the x values are between -5. And count over to the far right and find that the positive side of the domain would be up to 6. Now, for the range, I would do the same thing. I'd see that the range we are going to define as y is between the values -2 and +2. So now it's giving us this function transformed. 3 times h of x minus 4. State the steps we need to graph. So you'll notice that this 3 out in front is going to provide us with a vertical stretch. Once again, if you remember back to that those transformational notes, an a coefficient outside the function gives us a vertical stretch or compression. So in this situation, it's going to give us a vertical stretch by a factor of 3. We want to make sure that when we're graphing stretches and compressions that we graph the stretches and compressions first and do our translations last. In this situation, it's not going to matter, but in other functions that we use, it will change your domain and range values. So first, we would vertically stretch the function by a factor of 3, which this just means if you look at -5, -2, when x is -5 for this transform function, instead of going -2, I'll go to -6 because that factor of 3 times -2 would give me a -6. And then my next piece is that I would translate the function right 4, because this -4 is happening in the argument or directly to the x, and whatever's happening inside the argument, we are doing the opposite. So -4 would translate right 4. So I would stretch it. This y value is at 2. So by a factor of 3 would be at negative 6. And then I would translate right 4. And I'm going to do that for all key characteristic points. And I'm just saying points that I know. So in this case here, if I go up to this maximum height here, it's at positive 2. Once again, I would go up by a factor of 3, so up to the positive 6. And then I would translate right 4. This minimum value is at 1, so stretching by a scale factor of 3 would go, or I'm sorry, it's at negative 1, would go down to negative 3, and then translate 4. And then at this last point, again, it's at a y value of 2, so stretching by a factor of 3 would bring that up to 6, and then translate 4. And so then when I do this, I would simply stretch the function and translate it so that we could actually see the transformations. So after we have transformed this function, we need to state the new domain and new range and what's happened. So the domain is still going to be the x value, so we're going to define it as x such that, and in this case the lowest domain value is at negative 1, and the highest domain value is at 10. And so if you notice what our let's keep going with the range. So with the range, we're defining it as the y values, and the lowest y value is at a negative 6, with the highest y value at a positive 6. And so notice from this original domain to our new domain, from negative 5 to negative 4, that translation to the right 4, we have actually added 4, transforming our domain. So we could see that without even graphing it. Same with our range values. Our range values started at negative 2, and when we vertically stretched it by a factor of 3, we multiplied these range values all by a factor of 3. So from negative 2, my new range values go between negative 6 and positive 6. So now let's look at this last transformation. So this last transformation has a negative 1/2 as an a coefficient, so in this case it's actually a vertical compression. By a factor of 1/2. The negative causes it to be a x-axis reflection, with the minus 5 outside of the argument serving as a translation down 5. And so now that we've kind of defined what transformations are happening to this function, you on your own can graph these transformations and then state the domain and range of this child of h of x, which is just the transformed function. Thanks for watching.